welcome to my talk, Wi-Fi brokering. This is a talk for those who don't want to spend time cracking hashes and probably want to connect to some people's Wi-Fi or trick people into connecting to you so you can do horrible things to them or give them free internet, depending. Who am I? I'm Michael Kruger. I'm _CableThief on Twitter. I've been 4 years at SensePost, which is now Orange Cyber Defense. And I've been dabbling in Wi-Fi attacks for about 2 years of those. So what I'm going to discuss in this talk, the current attacks that are available to us around what we're going to be talking about, so specifically PEAP, new attacks that I've now created and presenting to you, building this thing, sort of the problems I encountered, other things we can relay using this, new capability that this enables you to do, and then defending against it, which might interest some people. So to start things off, I just want to give an overview of what PEAP is. So PEAP is protected EAP. It's some sort of Microsoft thing. And what it means is it's essentially an EAP authentication within a TLS tunnel. So the first thing that happens is the client device will set up a TLS tunnel with the access point. And then provided it accepts the certificate that the access point presents, so kind of how websites work, it will then, within that tunnel, do a MS-CHAP challenge response. MS-CHAP challenge response, we'll go into a bit more detail just now, but basically it can proves to both sides that the server knows the password and the client knows the password without actually passing the password over. And then the four-way handshake happens. The four-way handshake uses a key created from the previous steps. So that's what finally connects you to the Wi-Fi network. Cool, so challenge response. This now being the thing that happens inside the TLS tunnel. Consists of, first you send along your identity. So this is typically sort of your domain name. So mine would be Michael Kruger. The access point will then send along a challenge, which is 16 random bytes. You, as the client, will take that challenge, you'll generate your own challenge, put them together, and calculate a response using the password that you know. You then send that response as well as your challenge over to the access point. The access point does the same thing, and if it gets the same result, so it gets your response, then it knows that you know the password. It will then do a similar thing and send its own response to you, as well as the success, saying, okay, we validated your password, it's correct, you are allowed to connect to us. At which point the client will say, okay, cool, I can connect, but let's make sure that the server knows our password correctly first, and it will compare the response and do the whole thing again. So once again, both sides know whether the password is correct or not. So the current attack on this involves standing up a rogue access point. The victim, typically a rogue access point with the same name, the victim will come along and connect to it. They will have to accept your certificate so that you get into the inner phase, so phase 2. The challenge response will be performed in phase 2. The result of that challenge response is a hash, which, as you saw, when you are the access point, you get a piece of information. So you get 2 challenges, you get the piece of information. With all those things, if you keep pumping passwords into it, you can calculate the thing and you can validate it against that response that the server sent over. So it gives you a way to guess passwords offline, and eventually you can crack the hash and connect to the network. So this cracking is done with, typically I would do it with Hashcat, but there are lots of other tools. In Hashcat, you use the hash type netNTLM-v1, which is 5500. This is important later when I discuss some other ideas that I had. But for now, cracking MS-CHAP v2 is the same as cracking NTLM v1. Here we have just an example of the output. So we have the username, we have the response. So this is the bit that's calculated using the 2 challenges from both sides. We have an 8-octet challenge, and then we have the cracked password at the end. So this is pretty much the state of things now, and that's great. So you can get crack hashes and things for users. You can then go use those hashes, those passwords and things on mail and things like that. In the wired world, there's a second attack available that's not available in the wireless world. So the second attack is a relay attack. So what a relay attack is you position yourself between the client and the server. You trick the client into connecting to you, much like we were doing before, but rather than handling that authentication yourself, so for example, calculating the response and all those things, instead of doing that, you hand it off to a server that you know that you would like to authenticate against. So you can see in this diagram, the identity comes in. Rather than handling the identity, we pass it directly off to a server. The server sends back a challenge. Rather than handling that, we once again just send it to the client, so on and so forth. So this allows us to connect to the server while abusing someone else's authentication attempt. There are two tools that we would use to do this, well, that I personally use to do this. There's probably much more. The one is Responder, which is a great tool for tricking people, especially on Windows networks, into connecting to you. And then the other is Multi-Relay, which comes with Responder, or NTLM Relay X, which comes with the Impacket suite of tools, which is very nice. So the Responder bit tricks people into connecting to you. The Relay bit, the NTLM Relay bit, for example, relays to another host. So you trick the person connecting to the service, and then rather than handling that yourself, pass it on to the other host is the gist of it. So here's just an example of what that would look like. Responder calling out to people, tricking them into connecting to you. The person will then start connecting you, and they're actually talking to now NTLM Relay X, which in essence is them talking to a server in the back end. But at the final stage, when the server says success, you're allowed to authenticate. We tell the client, you're not authenticating, you got things wrong, try again later. They go off and hopefully connect to whatever they wanted to connect to in the first place without causing too much disruption to the user. But meanwhile, we've piggybacked off their authentication attempt and are now authenticated against the server to do whatever they wanted to do. For example, access file share or do some administrative action or something like that. So in the Wi-Fi world, we have that first portion. We can trick people into connecting to us. This is basically what a rogue access point is, just standing something up with the same name. But we don't have the ability to sort of handle that authentication, or at least not handle that authentication and pass it off to someone else to handle for us. So that's what I created. So what do we need to do this? Well, we need to be able to handle this whole PEAP exchange, and that means handling not only that relay in the middle, but also the two other bits, which is the four-way handshake as well as the outer TLS tunnel. So you can see here, I've kind of shown that we've got two separate TLS tunnels being set up, whereas we are only relaying that inner MS chat thing. And then we are setting up a different four-way handshake at the end. This is done using two components. So we'll see here that I have an evil server, which in this instance I chose to use host APD mana, which has got all sorts of other Wi-Fi attacks built into it as well. And that makes up this portion, which is the client being tricked, is connecting to us, and we're handling that TLS tunnel and that four-way handshake. But rather than handling that challenge response, we pass it down to the second portion, which is the sycophant, which is a modified version of WPA supplicant. And that is handling its own separate TLS tunnel and four-way handshake. So these two things work together to sort of ferry across that challenge response. And then at the end, hopefully we get a success from the server and we can connect. So building this thing, as you saw, I chose to use host APD mana, which is a modified version of host APD, as well as WPA supplicant, which is also very, very popular. And it is the supplicant that is used, or at least a modified version of it is probably used in Android. And yeah, as I say, very popular, and also makes a really good thing to edit, given how well supported it is across everything. So we now have the two different separate programs. They need to be able to talk to each other. I had a very complex system involving a state file and files to go back and forth. I've simplified that for you into sycophant writes to file, mana picks up from file. There's a state file which keeps track of where in the interaction each of the ones is. So if mana is in the challenge phase, it knows that it needs to inform sycophant that needs a challenge. Once it has that, it can say, okay, sycophant, here's a response. And it just uses files to do that. The primary reason for files was that I didn't want to learn how to do C interprocess communications and things like that. The excuse I gave as to why I'm using files is that it would allow me to easily do it over long distances. So for example, you can synchronize a file using all sorts of different tools, one on the server, one on the client, and you can do this. You can separate these things a lot better using the internet, for example. However, as you'll see later, I found a way to do that that doesn't involve the files, so it kind of invalidates that point. So here we have a demo. So put all that together, and this is what we get. So you can see here I have an interface called WLAN1, and it doesn't have an IP address. I then use AeroDump to show what's around us. There's an SSID called Black Cell, and it's of type MAJ, which means it's an EAP server. I'm going to tell you now it's a PEAP server because I set it up. There is a client as well. So I'm going to now cat the supplicant config file that we're going to be using. You'll see there, all we needed to do was put in the SSID, and you'll also note that the identity and the passwords are blank. Cool. And then we just run it. So sycophant, we give it the interface. This is the same interface I showed you earlier, which doesn't have an IP address. And then we give it that config file that I showed as well. Cool. Now it's waiting for Mana to give it the identity of someone so it can start connecting as well. But on the server side, sorry, we have Mana. We're using it on a different interface. We set the SSID to Black Cell, and we tell it that we don't want you to handle the authentication. Instead, we want you to write it down to files and communicate with this other program. And then we just run it using that config file. Oops, so EP enabled. Right, so now we have the evil client and the evil server. They're both waiting for someone to connect. I'm just going to force that client to deauthenticate from the network it is on using a deauthenticating frame and just setting it to Black Cell. So this sends a deauthentication on that same interface we ran AeroDump. And then you can see that hopefully the guy disconnects. Cool. And you can see phase 1, Stanley Jobson, phase 2. So obviously they've now accepted our certificate. You can see in the middle there's a hash that came through. I've highlighted there. And then another thing to note is that at the end, the client didn't fully, they didn't finish connecting to us, so they didn't perform the four-way handshake. On the sycophant side, you can see we got the identity from Mana, and we began this whole process. We got a challenge, we sent it through, and then we got the response from the client, finally getting an EAP success from the server itself, and then doing the four-way handshake. So now I'll show you that we have gotten ourselves a IP address of 10.0.40.77, and then I have set up a web server on the gateway to just show that we have internet access. Well, internal network access. Cool. Success. We can connect to arbitrary Wi-Fi networks, and we don't have to crack the handshake. Well, the hash, which is very nice. Something worth mentioning that the hash can be cracked in a reasonable time. It's just it's 3 DESs, and you can go through the entire key space, but it's still a lot of processing and a bit of a pain. So you won't be doing it on a Pi or anything like that. So why does this work? Once again, we have 2 separate TLS tunnels, and we have 2 separate four-way handshakes, whereas we have 1 challenge response. So the reason this works is the four-way handshake is the bit that actually connects you to the network at the end of all this, right? And the values that go into that four-way handshake are calculated beforehand through the other interactions we've had now. So unfortunately, the four-way handshake by default is only relying on the TLS portion, which we did ourselves, meaning we have the information to do the four-way handshake. We just need a way to trick the server into accepting us using that four-way handshake. So the way to fix this is to use something called crypto binding, which takes that outer authentication, the TLS, and the inner authentication, which is the MS chap, combines them together and uses them in the four-way handshake, making it so that the same person has to do both the TLS and the MS chap bit in that current situation, we only need to perform the TLS bit, and we can get any other third party to do the other bit for us, and we don't need that to finally connect. Cool. So the problems that I had while making this thing. So there's a lot of time that I could have saved by just reading the RFC. I would recommend that everyone reads the RFC. I'll go over some of those just now. And then the other problem was using only one platform. So I was testing against host APD all the time. And then when I finally tested against a Windows server, it kind of threw a hissy. But that was because I was accidentally overwriting 1 or 2 bytes too many. And then what I've mentioned already is just doing things in C is always a mission. And that's the reason why I did things in the file system, essentially. Cool. So first problem with the RFC, well, the one that I had from not reading the RFC, was the literature review. So when I first had this idea, I thought it was a very obvious idea, and I thought it must be done. I asked some of the people, and no one knew anything about it. And so I went looking. I found like some slides. It was a bit vague. It said it was possible. There was definitely no tool to do it. So searching around didn't find much, essentially. After I'd finished everything, made it, it all works perfectly. I go look at the bottom of the RFC. It's pretty much written in plain English. You can see in 7.4, section about man-in-the-middle attacks, explicitly says that where EAP is tunneled within another protocol that emits peer authentication, there's a potential vulnerability to man-in-the-middle. You can see, for details, see binding and MITM. I've already mentioned binding as a defense against this, and MITM, as you'll see now, with attack number 2. But yeah, so beforehand, before I made everything, put in all sorts of work, things. I thought I was revolutionary. Afterwards, turns out it was just there in the RFC all along. So the second attack that this enables is the ability to attack clients. So previously, what we would do is something called crack and add. So essentially what that is, trick someone into connecting to you, you get their hash, you crack them, you crack the hash, and then you put that in your EAP file, your EAP users file, and then when the client comes around a second time, hopefully you get such an opportunity, they will connect, you will be able to validate that final response, given that you now know the password, and they will connect to you. With iOS devices, which is now fixed, by the way, you could do the same thing, and iOS was not validating that final part of the challenge response. So iOS, Mac, whatever. This lets you return only just an EAP success, and then you can send along an invalid response, and the iOS device would not check it, and they would just end up connecting. So that allows iOSs to get more internet, but you don't know where you're getting that internet from, essentially. So just going through the current attack, not against the iOS, you would stand up a rogue access point, you'd trick victims into connecting. Once again, they'd have to accept your certificate. You would perform the challenge response, you capture that hash, you would then go crack that hash, and then try and get the client to connect again. So it's not very real time, unless they have a really, really bad password, which you can always hope for as well. So here's an example of what that sort of interaction would look like. The client would send along its identity, server sends a challenge, client calculates own challenge, calculates response, sends it along. Server sends a bogus response as well as a success, saying, yes, you can connect to me, you've authenticated, please trust this response. But the client, of course, in general, won't trust that response. It would try and verify it, it would fail, and then the client wouldn't connect. So you'd kind of be stuck unless you had the client's password, which is where the crack and add comes in. So with relaying, you can prove that you know the password, or at least you can prove that somebody knows the password, not necessarily you. So once again, you set up your TLS tunnel, trick the person into connecting to you, they initiate the TLS, you start authenticating to a random server somewhere that does know the password. The challenge response ensues. The server will send back a correct response because it knows the password. You can then pass that to the user. And then once again, because the four-way handshake is calculated using only stuff from the TLS tunnel, you can then both sides have all the information needed to set up the four-way handshake and connect finally. So that means the user can connect as well as you just connecting to the access point as previously discussed. So demo time. Let's go again. Okay. Cool. So once again, I'm showing you that WLAN1 doesn't have any IP address. And then I'm going to run error dump and see that the black cell is still there, type managed, which is EAP, and there's a client connected. Once again, we set up sycophant the same way, so no password or anything, setting the SSID. Typically, you'd want to set the SSID to something that the client is connected to already. And then we run Mana. So now I'm using a tool called Berate AP. I've just given it some flags. So Berate AP is a tool I wrote to sort of dynamically generate Mana configs because I got tired of writing them. So the things to point out here is that we're once again passing it the sycophant flag, saying that we want it to relay the authentication rather than to calculate things itself. We want it to return an EAP success. So it's going to, regardless of what it thinks, is going to send it back an EAP success. And then in combination with the supplicant flag, the sycophant flag, it's going to send a correct one. Once again, we give it the certs. We say run it on the second interface and run it on the first interface and call it black cell. Okay, once again, we're going to have to send a deauthentication frame to get the user to disconnect. In this instance, the user is a bit stubborn, so it's time for my water break. And then now we wait. Once again, we're just waiting for the user to connect to us so that we can perform the TLS. They accept our certificate, send us all the things we need. Cool. Send another deauthentication, and now the user comes through. So you can see the identity came through, and then you see the same hashes as you saw before, but at the end is different. You'll see that an accounting session started, and there's an authentication, the four-way handshake was performed, and the user actually connected to us. On the supplicant side, sycophant side, it's the same as before. We're also successfully connecting to the access point. Cool. So success validation, that's the validation that was sent back, so the correctly computed one. Once again, I run T-Shark just on the interface for the access point, and you can see that there's an Apple device sending ARP requests, so showing that they've properly connected to us. And yep, cool. Right, so success again. We can randomly trick people into connecting to us, and this allows us to do all sorts of crazy things. So the nice thing about this is we can trick them into connecting to us while using their authentication to connect to the legitimate server. And that's what Berate was providing me in that instance, was it was setting up all the networking between those two interfaces for me. So that a user, the person that we've now tricked into connecting to us, can still reach things on the legitimate access point. So very nice. So I discussed distances before, the reason I put things on a file system. But turns out host APD, and by extension host APD Mana, has its own built-in Radius server. Now Radius allows you to do EAP things over the network, so that the thing that you're authenticating to doesn't necessarily have to do all the authenticating. So it sends along, it talks Radius to another server. So to do this over a long distance, you set Mana or host APD Mana as a Radius server along with a sycophant. So they need to still talk together using the file system, but you can set up an access point to use your Radius server and point it at the Radius server, obviously. So provided these two things have a network connection between them, you will be able to do this attack over a long distance. The idea behind this was that you can, while someone's sleeping, for example, you can go throw a Raspberry Pi in their garden, and hopefully if they have a phone or their laptop, it'll automatically try and connect to your device, and you can relay that while you are on site at near the corporate access point, and so then you can connect to it. The other thing that this lets you do is obviously you don't have to be near the access point, so things like sort of rogue access point protection, and you're not competing against a corporate access point, which has probably much better signal than your little alpha card. So you don't have to go through all that trouble. That was the idea behind that. So it is possible. The next idea I had was, given that NetNTLM v1 and MSChap v2 crack the same with Hashcat, so they both use hash type 5500, can't we relay from the wireless world to the wired world? So once again, using the idea of throwing a Raspberry Pi in a sysadmin's garden, you trick their device into authenticating to your access point, you relay that authentication, and you pass it off to an SMB server, which will let you ride their authentication. So how we did it on the wired world, but sort of going from wireless to wired. So very cool idea. And this was actually the original plan I had when I first thought of this idea, given that at the time I thought, okay, I can relay people, but the client doesn't want to give me Wi-Fi, so maybe I can do something with this. But you'll see why I can't. So I compared the hashes, they look the same. Challenge 8 octets, response 24 octets. You'll see in the NTLM v1 one, there's an LM response there, you can safely throw that away. But the NT response 24 octets, challenge 8 octets as well. So they line up. And so once here we get to the point where the not reading the RFC bit me again, in that I did not read through it. So I immediately went into implementation. I grabbed Impacket, the same project that gave us that nice NTLM Relay X I mentioned earlier. So I programmed it to use NTLM1 all the time, as well as my whole complicated state file and challenge response file structure. And then it turns out, looking through the code, reading from the file, my file for the challenge had 16 bytes in it, whereas I was only looking for 8 bytes. So this was a bit of a problem, as I can't fit 16 bytes into 8 bytes. So then I started investigating. And if I had read the RFC, I could have seen at the bottom, there's all sorts of pseudocode provided. And let me simplify this for you. MSChap takes two 16-octet challenges, combines them together in a SHA, and takes 8 bytes from there. And then NTLM v1 kind of just passes over 8 bytes. So given that what they're passing over the wire is different, you can't relay what they're passing over the wire from one to the other, because the one would be expecting 8 octets while the other's providing 16 octets. So that sort of ruined my idea, wasted a day doing all that implementation and things like that. And if you remember my complicated state file diagram before I simplified it for you, it was a bit of a pain reworking out how I did all this stuff. So the takeaway, read the RFC, very helpful. So now we go on to the defense. So the main thing here, I think, that you should take away is you should probably not use PEAP. So given its very nature, users are able to set it up themselves, given that they know their passwords. So a user is always going to want to get internet and get onto the network, where that might not be ideal, because when they're setting up their own wireless devices, they're more likely to click "Don't validate this certificate," because it might be that they don't have the certificate on hand and they just really want Wi-Fi. So that's the first failing. The second thing is using a single strong method is preferable. Once again, talking to PEAP, if you use purely certificates, so for example, EAP TLS, a user is not going to be getting that certificate and setting it up and things like that. They're probably going to have to go to their IT team and get that sorted. So if you really, really want to use PEAP and you don't mind that you'll be giving away your hash, you can enable cryptographic binding. So this defense steps in when people aren't validating their certificates, and maybe your users have really strong passwords that people aren't going to be able to crack. But once again, I said that MSChap, you can go through the entire key space. So still not really good. But if you enable crypto binding, at least people can't relay arbitrarily to your things, and they would then be forced to go through that mission of cracking the hashes. Cryptographic binding, once again, just sort of binding the TLS layer to the MS-CHAP layer and requiring that the same person did the authentication. Here we have an example of a Windows server where you can enable crypto binding. So disconnect the clients if they're not wanting to do it. So that stops people authenticating unless they crypto bind. And then here we have the client perspective where disconnect if the server isn't presenting its TLS is not crypto binding. So you have to enable this on both sides. So the person that's enabling it is the one that's protecting themselves. So bear this in mind. So if only the server is crypto binding, you can attack the client. So the client will still connect to you, because when they start connecting, you don't have to present crypto binding. But when you connect to the server, you say, okay, I will crypto bind, but you just relay the inner authentication as usual. So that gets you the correct responses you need. On the client side, so the crypto binding is enabled on the client, you can still attack the server. So when you present your rogue access point to the client, you say, don't worry, we're using crypto binding. While the client won't connect to you, you will still then be able to relay the authentication and connect to the server. So future work, given COVID, I've had lots of time to work on these sort of things. And my idea was looking for more things to relay. So MS-CHAP is actually quite popular. It's used in a lot of things. And the next place I found it most widely used is in VPNs, specifically Microsoft's SSTP and PPTP. And I've already begun work into relaying from Wi-Fi to that. So in future, you'll be able to trick people into connecting you, and then you would then be able to connect to their VPN, which gets rid of the locality element where you need to be near the access point to connect to it. Here's my one meme, which I think represents a relay attack. As you can see, they're redirecting the water somewhere else. And that is my talk. So thank you, and any questions?